I start the recording. Okay, let's start the plenary sessions. The speaker is Paul Sutcliffe from Durham. I hope he would be the Paul. He'll talk about the ADHM construction of Skyrmions. So please start.
Yeah, thank you very much for the invitation to speak. And I just want to emphasize, yeah, feel free to interrupt if there are any questions that you want to ask. I'm going to talk about Skyrmions. And I was asked to make at least the first half of the talk, so review material. So I'm going to, the topic I've chosen to review on Skyrmions is regarding the various approximations that you can make to try and study them. So that will be, most of the review will be on that. And then I'll tell you about some new stuff towards the end. And that's work with Derek Harland. And it's available as a preprint on the archive from about a month ago. And that's about the ADHM construction of Skyrmions. So this is a new approximation for Skyrmions. And it's based kind of on the ADHM construction of instantons. And if you don't know about that, then hopefully you will do by the time I get to the end of the review material. So here is the plan of attack. So I'll give an introduction. So I'll try and give you the talk in picture format in 5 minutes. So without any details, but the idea of what the talk's about. Then I'll give a few more details. So I'll briefly review Skyrmions, tell you what you need to know about them. And then some of these approximations that I mentioned. So rational maps, and I'll have to tell you a little bit about instantons and ADHM so that you can understand one of the other approximations, which is due to a Manton. And then finally, I'll tell you about our new approximation and summarize. So here in picture format, I'll show you a movie that's going to explain something about what I'm trying to tell you about in this talk without you having to know any details. So Skyrmions are topological solitons in 3-dimensional space. So here you can see a load of lumps. You don't even need to know what I'm plotting. You can just see there are some lumps, and each lump is a soliton. It's a Skyrmion. And you can see if they're far from each other, then they look like a ball. So I've got a video with 2, 3, and starting with 4 balls. So 4 solitons, 3 solitons, 2 solitons. And I'm going to show you what happens in numerical simulations of some nonlinear partial differential equations that come from the Skyrm model. So these are very old numerical simulations that I did with Richard Batty in the last millennium. And what they'll show is that here I've just plonked down these solitons. They're going to attract each other. And when they attract, they'll merge and form something symmetric. And that's what I'm trying to understand. These are numerical results, and I'm trying to understand in this talk something about this process using some kind of analytic approximation. So here, let's start the movie. And here you can see that the solitons, these Skyrmions, attract each other. And as they get close to each other, they deform a lot. So they deform and they make very symmetric looking configurations. In fact, those are the minimal energy configurations for those numbers of solitons. But they came in with some kinetic energy, so they scatter through those things and emerge back out. So what I'd like to understand is, what are these minimal energy configurations, and how to understand what happens to Skyrmions all the way from being sort of well separated to coming together, overlapping, forming these symmetric configurations, and then going back out. So that's the aim of the talk. So how can you do that? All right. So this is what we're aiming at, trying to be able to describe somehow, without having to use full numerics, configurations that look something like this, plus well-separated balls that will eventually come in and look like this. So you might ask, how did I start with those numerical simulations? I had some sort of well-separated 1 Skyrmions. That's not too hard. That's something called the product ansatz. So when I come on to describing a bit more of the details of Skyrmions, you'll see that they're described by a matrix. And so if I've got if I can describe one skyrmion, I have the matrix of that. If I've got another skyrmion far away, that's another matrix, and I can just multiply the two matrices together. That's the product ansatz. And that works well as long as the things that I'm trying to put together are well separated. So here I have two single skyrmions down at the bottom with a tick showing that that's kind of a product ansatz. It works well if I've got two well separated things. But we saw that as the two skyrmions come together, they make this kind of donut shape. That's not well described by the product ansatz. As you bring these product ansatz works well when the things are separated, but if you try to bring the things too close together, it doesn't give you what you want. It doesn't give you something that looks like that. So that's the simplest possibility of some kind of approximation. Another approximation that I'll tell you about is called the rational map approximation. That works well in the opposite regime to the product ansatz. So if all these skyrmions are sort of on top of each other, like we saw when they merged and they make these symmetric shapes, that's when this rational map approximation works well. It basically says that you sit at the center of this complicated skyrmion and you look around to see how the field varies in the angular directions. And those angular variations are specified explicitly using a rational map, which is a ratio of polynomials. So that works very well, providing all the skyrmions are on top of each other, making something like this cube, for example. Because you can sit right at the center of that and look around to see how the angular dependence varies. It doesn't allow a description of well-separated skyrmions, because you have to sit at the center of all the skyrmions, and you can't do that if they're in different places. So the tick next to the cube shows the rational map approximation works well when all the skyrmions are on top of each other, but can't describe pulling the skyrmions apart into individual ones. So the only currently known approximation that works well to describe both situations, so skyrmions that are far apart and on top of each other, is called the Diamantin approximation. So that can describe all the things that we want. How does that work, roughly speaking, is we're interested in skyrmions that are solitons in three-dimensional space. The starting point for the Diamantin approximation is to consider some solitons in one higher dimensional space. So solitons in four-dimensional space. And the solitons that we're interested in are called Yang-Mills instantons. So you might say, that seems a bit crazy. You're interested in something in three space dimensions. It's too hard, so you go to something in four space dimensions. Doesn't that make things harder? But in fact, it makes things easier because these Yang-Mills instantons in four-dimensional space, they're solutions of an integrable system, which means it has special properties that can allow you to construct solutions. It's also BPS, which means that there are no static forces between them. So you get a large space of instanton solutions. One of these integrability properties means that there's a construction for the solutions in terms of something called the ADHM construction. That's a way to construct these instantons just using linear algebra. So although the Yang-Mills instantons live in four dimensions, not three, they're actually easier because there's a way to construct them. So you might say, are we not done? We can understand all these things, but the sticking point here is in going from the instanton to the skyrmion, the Diamantin approximation requires solving a differential equation. You basically have to solve a differential equation in the extra fourth dimension. And unfortunately, you can only explicitly solve that differential equation for a spherically symmetric skyrmion. So although it does in principle allow you to write down approximations for all these skyrmions I'm interested in, you have to do a bit of the step numerically. You have to solve that ordinary differential equation numerically to go from the instanton to the skyrmion. And that's the step that the new approximation will cut out. So the new approximation, again, can describe all these configurations of whether they're well separated or on top of each other or everything in between. but it goes directly from the ADHM data, so the thing that you need to construct the instanton. You don't actually have to construct the instanton. You can go directly from that data to the skyrmion without having to solve any differential equations. And it will produce for us some rational approximations. So not to be confused with rational maps, the word rational in this context will mean that the approximations will be rational functions of the Cartesian coordinates. So that's roughly speaking the plan of the talk. I'm going to explain a bit about skyrmions, a bit about all these approximations, and then tell you about the new one. Are there any questions before I delve into some of the details? If not, then let me say that I'm going to tell you only about the things about skyrmions that I'll need for the talk. So that's just about classical soliton solutions and approximations. I'm not going to say anything about the physics or about lots of other things, but everything that I'm going to talk about plus more is contained in full detail in Nick Manton's book from last year called Skyrmions, Theory of Nuclei. So if you want to look up any of the details or get some understanding of the physics behind this model, everything will be in here except the new approximation that I'm going to tell you about. So the only thing I'm going to say on the physics side is that the reason for being interested in skyrmions is that they model nuclei, and the number of skyrmions, so the number of solitons you have around, is identified with the number of nucleons in the nucleus that you're interested in. So that's the motivation for being able to understand these configurations. You want to understand things like the forces between these skyrmions, the binding energies of them. So we saw that the skyrmions come together and form configurations that overlap. They're lower energy than being well separated. In other words, there's binding, which is good if it's going to be a theory of nuclei. And so that's the motivation for wanting to study all these things, but there's all kinds of other details that I won't have time to tell you about. That's a sort of different talk, but you can find them in this book. So here's what I'll need to know, what you'll need to know about skyrmions. So we're talking about topological solitons in three-dimensional space. The field of the theory is an SU2 matrix. So that's called the Skyrm field. I'm only going to talk about static, so time-independent configurations. So a Skyrm field U will be something that depends on the three Cartesian coordinates of R3 and is SU2 valued. So it's an SU2 matrix defined throughout R3, with the boundary condition that this matrix becomes the identity matrix as you go off to spatial infinity. That boundary condition compactifies space so that topologically space is a three-sphere. It's a three-sphere of infinite radius, if you like. And since SU2 is basically also a three-sphere, there's a topological charge here, which is good because we're interested in topological solitons. This topological charge is an integer, and it tells you how many times you cover the target three-sphere as you move throughout space. So how many times do you cover the space of SU2 matrices as you move through space once? So that integer is called the topological charge. I'll denote it by B because physically it's the baryon number. So if you're interested in studying a nucleus with B nucleons inside, then that B is this baryon number that you're interested in. So that's your number of skyrmions. And you can write down an explicit expression for what this baryon number is. The R's here, there are three of them. They're the currents associated with the SU2 matrix. So I can differentiate my Skyrm field, the SU2 matrix, with respect to any of the three Cartesian coordinates and multiply the right by the inverse of U. That gives me something that's in the Lie algebra of SU2. So I've got these three algebra value currents. And to calculate the baryon number, so just think of R as being like the derivative of U. To calculate the baryon number, I multiply all the three R's together and integrate, basically. So the energy is constructed in suitable units, it's given there, is constructed from two terms. So the first term is a sigma model term, so it's just something that's quadratic in derivatives. So it's got r squareds in it. And then the other term is called a Skyrm term. That is quartic in derivatives. So there's 4 r's in there. So you can see, roughly speaking, if you've got something that's quadratic and something that's quartic, you could try and complete the square, and the cross term would then be cubic. And that's where this energy bound comes from. You sort of complete the square here, and the cross term will be the baryon number. So you find that there's an energy bound. So in the units I'm using, the energy is always greater than or equal to the number of skyrmions that you've got in your system. So what we're interested in is writing down, so first of all, you might be interested in the simplest thing, which is let's try and write down the lowest energy configuration for each B. So take B equals 1, 2, 3, 4, for example. We know the energy is greater than or equal to 1, 2, 3, 4. What is the lowest possible energy? What does the configuration look like? B equals 1, 2, 3, 4. So let's start with the simplest case, B equals 1. So B equals 1 is called the hedgehog skyrmion. It has the form that's written here. So F just depends on the radius. And then there's the Cartesian coordinates as a vector dotted with the vector of Pauli matrices. So that's an SU2 matrix. So I showed you the picture and I said that the charge 1 skyrmion was spherically symmetric. So you might think I'm lying here because the U that I've written down is not just a function of the radius. It's got some explicit x's in there. So by symmetry, I'm using the following fact, that there's an isospin symmetry in the model, which you can check. If I take U and I conjugate it by any fixed element of SU2, so multiply on the left by any matrix and on the right by its inverse, that doesn't change any of the physical quantities like energy density or baryon density or anything like that. That's a symmetry. So why is this field I've written down here spherically symmetric? So it's spherically symmetric in the sense that if I do a spatial rotation, then U will change, but I can undo that change by applying an isospin rotation, which doesn't change any of the densities. Okay? So it's in that equivariant sense that I have a symmetry. And that'll be true of all the symmetries that I talk about. It means that when you do some kind of spatial rotation, you can undo it with one of these isospin isorotations. So once you've specified this hedgehog format, so it's called hedgehog because if you think of the sort of directions in which that vector is pointing that's dotted with the Pauli matrices, it's pointing sort of directly away from where the skyrmion is. The skyrmion here is sat at the origin, and these vectors point directly away from the origin. So they point out like spines on a hedgehog. So given that ansatz for B equals 1, the thing that you need to find is this real function that just depends on the radius. So this f of r profile function. That's telling you sort of how quickly you approach the vacuum as you move away from the center of the skyrmion. So the skyrmion is centered at the origin where this profile function is pi, and you see that means that U is minus the identity matrix, which is as far as you can get from the vacuum. That's why this is the center of the skyrmion. And then f is a monotonically decreasing function that goes to 0 as you go off to infinity. So if f goes to 0, then U will go to the identity matrix, which is the right boundary condition. So you can take this hedgehog form and stick it into the energy expression that I had previously. And that will then give you an energy expression for what this profile function is. So it's now a sort of one-dimensional problem. You have to find this profile function, f of r, that minimizes this energy, subject to the boundary conditions that it goes from pi to 0. So fortunately, here's where we hit the problem that skyrmions are not as nice as some other solitons like BPS monopoles or the Yang-Mills instantons I'll talk about later, is that you can't solve anything exactly. Even for this charge 1 this profile function can only be obtained numerically. So you have to do some numerical calculation and find what this profile function is by minimizing this energy, equivalently solving a second order ODE for F. And if you do that, you'll find that the energy is about 23% above that bound. So we said that the energy has to be, I've got one skyrmion here, the energy has to be at least 1. Well, it's about 1.23 something. So you don't attain the bound. That's good because that leaves enough room for some kind of binding energies. And if you want to know what does the profile look like, well, it's kind of what you might guess. So numerically finding the profile function gives you the black curve here. So you see it starts off with pi and goes to 0, and it does it sort of monotonically decreasing. I'll explain a little bit later what the other curves are, but you can see they're all quite similar. The black curve is what you get by numerics. Okay. And I mentioned this product ansatz. So if now you've calculated your one skyrmion, so you've found this profile function, you could describe something that looks like two well-separated one skyrmions by just multiplying the two U fields together. So you take the U field of a skyrmion located somewhere using the hedgehog ansatz. You take the your numerical profile function to compute that. You take another skyrm field that represents a skyrmion that's quite far away from your first one and multiply these two skyrm fields together. That again is an SU2 matrix, and that will look like two well-separated ones. But as I mentioned, it doesn't work if you try and bring these skyrmions close together. Then it breaks down and you don't get something like you would do if the two skyrmions were allowed to just numerically approach each other and form, say, example, a torus. Okay. Any questions about the simplest charge 1 skyrmion before I move on? If not, then let me tell you about this approximation that works when the skyrmions are on top of each other. So this is called the rational map approximation. And so to introduce it, I'm just going to show you the one skyrmion again. The one skyrmion using the hedgehog ansatz, but I'm going to rewrite it in terms of completely different variables. So when I wrote it before, I was using the Cartesian coordinates, so x, which are x1, x2, x3. I'm going to rewrite that using spherical polar coordinates. So I already had an r in there. So now I'm going to exchange my x's for r, thetas, and phi's in the usual way. So theta and phi being the angular coordinates on the sphere. And then I'm going to exchange theta and phi for a complex coordinate z, which is the Riemann sphere coordinate. This is just the thing that you get by stereographic projection. So if you take a point on the sphere given by theta and phi and you do stereographic projection to the complex plane, that's what z is. So if I use these new variables, so r and z, I can write down the same hedgehog ansatz that I wrote down before, but now it looks a bit different in these variables. So you see it's exponential something. You can recognize there's an f of r. So here is the f of r. Here's the profile function I had before. And then all the other bits in the matrix are just a more complicated way of writing the thing that looked a bit like x dot tall before. So the Cartesian coordinates dotted with the Pauli matrices. I've just explicitly written some matrix here. And W is just Z. So if you take W, this complex field, and replace it by Z, this is exactly the hedgehog ansatz that I showed you before. I've just written them in these funny variables. So why would I want to write it like this? Is because it now suggests a way that you might generalize this to something beyond the charge 1, so beyond the 1 skyrmion. And that's that this W equals Z. Well, think of W as a function of Z. Well, it's a degree 1 rational map. So Z is a complex number, but it can be infinity as well, because it's stereographic projection. So it's on the Riemann sphere. It's a CP1 coordinate. And so is W. So you can think of W as Z as a map between Riemann spheres. So a map from CP1 to CP1. And what we've just done here is taken the simplest possibility. You could just take W equal to Z. That's a degree 1 map from CP1 to CP1. The rational map approximation is to say, take exactly the same thing, but we're going to allow W to have a higher degree than 1. So we're allowed to do. If we want to describe a skyrmion with baryon number B, so B skyrmions, we're going to take a degree B rational map. So we're just going to generalize the W equals Z to W being any polynomial of degree in Z of degree B over any other polynomial in Z of degree B. So a rational map of degree B. The alphas and betas can be any complex numbers. The only constraint is that you better make sure that there are no common factors in the top and bottom. So if you do that, then you generate your skirm field. Instead of it being the charge 1 hedgehog, it's no longer a hedgehog, and it's no longer got charge 1, it's got charge B. So if you take that approximation and stick that form that I showed you into the energy function, again, you can do the integration over the angular coordinates and just get a sort of one-dimensional problem for a profile function. And you see that the energy looks very similar to the energy I had before for the profile function. There's only 2 changes. So one change is that there was a number 2 here, and now you get 2b. So the profile function is going to change from what it was before because you're minimizing a slightly different energy. Because this number here is now, there's a b in here instead of a 1 as before. And there's also a new coefficient that used to be 1 that is now called I, that appears over here. And I is something that depends on which rational map you choose. So the B didn't depend on which rational map, it only depends on the degree here. So the only term that cares about which rational map I choose is this one here, that has the I in front of it. And this I, you can see, is multiplied by something that's positive. So if you want to make this energy as small as possible, you should try and make I as small as possible. And here's the expression for I, it's given in yellow. So it involves taking whichever rational map you've got and differentiating it and doing some integral. Remember, Z is a Riemann sphere coordinate. This factor here, this Jacobian, that's just the area element on the 2 sphere. So you're just taking this rational map, differentiating it, and some combination of its derivative and itself integrate over the sphere, the 2 sphere. So that's some number. And you want to make that number as small as possible if the rational map is going to have the least possible energy, this rational map approximation. So you can think of I as an energy function on the space of rational maps. And what this does for you then is say, okay, you pick a B, then I can find out which rational map minimizes its energy function, and then that will be the rational map that I want to take for minimal energy. So you can do that. Here are the answers for B equals 1, 2, 3, and 4. So B equals 1, if you try to minimize, you find W equals Z, which is what we had before for the hedgehog field. And if you do it for 2, you find Z squared is the rational map. And that gives you a very good approximation, if you take that, to this minimal energy charge 2 skyrmion. So this donut. Charge 3, you find this map, degree 3 map, and that's the unique map at that degree with tetrahedral symmetry. So we saw when the 3 skyrmions come together and deform and sit on top of each other, the very symmetric configuration had tetrahedral symmetry. So this rational map approximation gives you a good approximation to that and tells you why the map should have tetrahedral symmetry, because that is the energy minimizing rational map. And similarly, charge 4, degree 4, then you find the unique map of that degree with cubic symmetry, telling you that the minimal energy skyrmion should have cubic symmetry, and indeed it does. So all these approximations, of course, a set of approximations, which means that the energy is not going to be exactly the same as what you would get by doing full numerical simulations. And the error tends to be something around sort of 2%. So the energy tends to be about 2% higher than what you find if you do numerics. So Here I've given the numbers, for example, for B equals 2. The error is about 2.5%. So this is, we're happy with errors of a couple of percent. We tolerate those. And so using this approximation, we get good approximations to all these minimal energy skyrmions and others, as long as the skyrmions now are sat on top of each other and we can describe them with a rational map approximation. But there are no degrees of freedom in this approximation to describe pulling apart these skyrmions into well-separated individual ones. So that's the tick next to the cube. We can do things like that, but we can't do things like 4 well-separated skyrmions that would come in and form this cube. So that's, I've told you about 2 of the approximations I had on my slide. I've told you about product ansatz and the rational map. To tell you about the Atiyah-Manton approximation, I'll have to first tell you something about Yang-Mills instantons because it uses that. So Yang-Mills instantons, we're just thinking of these, so SU2 Yang-Mills in R4, so we're thinking of these as just static solitons in 4 space dimensions. So the field of Yang-Mills theory, I have a gauge potential, a mu, so that's SU2 valued, and mu runs over all 4 space coordinates now, 1, 2, 3, 4. Then F is the usual non-abelian field strength that you construct from your gauge potential. So it involves differentiating and taking a commutator. And the Yang-Mills energy is this expression that involves F squared. So it's the usual Yang-Mills energy, if you're familiar with that, involving an F squared term. You note that F looks like a derivative and A is a gauge potential, so that's also like a derivative. So you can see from this that this energy is sort of scale invariant. F squared scales in the opposite way to the volume element R4. So if I take a configuration and I rescale it, it doesn't change its energy. There's an energy bound like there was for the skyrmions. The energy is bounded, is greater than or equal to, in the units I'm using, greater than or equal to number of instantons you have. The instanton number is like the soliton number from before, and there again, there's an explicit expression for it. Again, involves sort of F squared, but with an epsilon totally antisymmetric tensor thrown in. So the fact that instantons are mathematically nicer than skyrmions is the fact that you can attain this energy bound. So you can find configurations whose energy are equal to n for any n, and they're obtained by self-dual fields. So fields that solve this first order equation so that F is equal to the dual of F, which is F with an epsilon and a factor of half. And there's an 8n dimensional moduli space of charge n instantons. So there are lots of these. Where does the 8 come from? Why is it 8n? Well, if I just think of a single instanton, I could put it anywhere in space. That gives me 4 parameters because space is 4-dimensional. It has any size because I've already told you that it's scale invariant. So that's an extra parameter, that's 5. And then there's an internal SU2 orientation. So that gives me another 3. So a single instanton has 8 parameters. And if I've got charge n instanton, I essentially have 8 parameters for each instanton. That description works well when they're well separated. And then as they come together, I still have 8n parameters to vary, but they're like skyrmions in the fact that they deform each other and you get complicated shapes and so on. So think of these as sort of like a mathematically nicer version of skyrmions in one high dimension. And then this ADHM construction that I mentioned that we'd need to know about, so that's due to Atiyah, Drinfeld, Hitchin, Manning, is a way to construct those instantons using just linear algebra. So if you want to construct an instanton, your starting point is just a matrix whose size depends on the number of instantons that you want to find. And it's a matrix of constant quaternions. So you take a symmetric n by n matrix of quaternions and you stick on top of it a row of n quaternions. That's what's called ADHM data. So it's just some big matrix of quaternions. And to be ADHM data, it has to satisfy the constraint that if I take this matrix and multiply on the left by its quaternionic conjugate transpose, then that has to be real and non-singular. So that will be some m by m matrix. In principle, it could have lots of quaternionic bits in it, but they all have to vanish. So there's a correspondence between instantons and data of this type. And the ADHM construction tells you explicitly how to find how to calculate the gauge potential of the instanton from this matrix. And here's what you have to do. There are 3 steps. So somebody gives you the ADHM data, they give you this matrix of quaternions. The first thing you do is you have to get space involved. So you have to get your R4 of space into the mix somehow. The way you do this is by introducing it into the square bit of that matrix, by plugging in the identity matrix for the square bit, multiplied by the spatial coordinate thought of as a quaternion. So I've got 4 space coordinates. I can identify a point in R4 with a quaternion, and that's what I stick in. That's how I get space involved. So step 2 is where the linear algebra comes in. I have to find the kernel of this ADHM operator, this delta. In other words, I have to find psi, which is an n+1 component column vector of quaternions, which has unit length, so psi dagger size 1. And when I multiply psi dagger on the left of delta, I get 0. So that's just a problem in linear algebra, right? Find this vector psi so that psi dagger delta is 0. And then step 3 is once you've found that psi, you have to differentiate it and multiply on the left by psi dagger. So that's step 3. That gives you an explicit expression for A mu. So everything here was involved quaternions, and the A mu that you write down there is a pure quaternion. And I said that I was interested in A mu being taking values in the Lie algebra of SU2, but a pure quaternion is equivalent to something in the Lie algebra of SU2 because I can just represent my quaternions as use a 2x2 matrix representation of quaternions in terms of Pauli matrices. So I can identify a pure quaternion with an SU2 valued field, the algebra of SU2 valued. So that's the construction. Somebody gives you the data, you just follow these 3 steps and you construct your gauge potential. So now I can tell you about the Atiyah-Manton approximation. So the Atiyah-Manton approximation says that you can approximate skyrmions by taking the holonomy of an instanton. So here explicitly, what does that mean? It means you have to solve some differential equation in the 4th direction. So I've split up space. I've broken the symmetry a bit by splitting up the R4 of space into R3 and the X4 coordinate for the extra dimension. So the differential equation that you have to solve is the one in yellow here. So as input, you put in the gauge potential of a charge n instanton. You put in the A4 component into this differential equation. So you have to solve this differential equation along the X4 line. So you have to do this at each point in space, 3-dimensional space that you want your skyrmion. You solve along a line in X4, this differential equation for omega, for this holonomy, where you're starting at X4 equals minus infinity with omega being the identity matrix. That's your initial condition. And then you solve this differential equation along the X4 line till you get all the way to X4 is plus infinity. And then the omega at that point is what you identify with your Skyrm field. So you've solved the differential equation along the X4 line. And this is a matrix differential equation. It's an ordinary differential equation because you're just solving along the X4 line, but it's a matrix ordinary differential equation. And that's why it's difficult to solve when you can only do it in a spherically symmetric case. But what Atiyah-Manton showed is that this gives a Skyrm field with the baryon number being equal to the instanton number of whatever instanton you stuck in to create your differential equation. So this gives a way of approximating. So you have to solve this differential equation. So somebody gives you an instanton, you solve this differential equation, the gap gives you an approximate skyrmion, And if you choose the right instanton, you'll get a good approximation to the skyrmion you are after. Let me give you the simplest example. So p equals 1. Let's recreate our approximation to the hedgehog ansatz. So you take an n equals 1 instanton. I'm going to place it at the origin. And I remember I said that things were scale invariant. So this instanton will have a size, an arbitrary size, a real parameter. I'll call it lambda, positive. So if you do this procedure, you can solve this differential equation in this case, because it's charge 1 and spherically symmetric. And you will get a profile function that's explicit. It's given there. So it still contains as a parameter the size of the instanton. So I said you have to choose the right instanton. In this case, it involves choosing the right size for the instanton. And if you choose the right size, so some value of this scale parameter lambda, then you find that this is a very good approximation to the 1 skyrmion, and the error is less than 1%. So it gives you a hedgehog skyrmion with the profile function, and that's what this red curve is shown here. That's the Tiamantin approximation for a 1 skyrmion. And you see it's fairly close to the black curve. So it gives you a good approximation to the thing that you can only calculate numerically. It's an analytic approximation, and its energy is within 1% of the energy of the true skyrmion. Okay. Maybe I'll skip why it works. You might ask why this approximation works, and you can understand that in terms of thinking of this as a sort of leading order term in some exact expansion. But I think for reasons of time, I'll skip that. So let me say the good things about the Tiamantin approximation are that the instanton moduli spaces induce spaces of skyrmions. And they include good approximations not only to these known minimal energy skyrmions, but also to well-separated ones and everything in between. So by taking families of instantons and calculating the solution of this differential equation, you can get good approximations to families of skyrmions where the skyrmions start out well-separated, they come in, overlap, form something that's good approximation to the minimal energy one, and go back out. The reason that's important to have something like that is if you want to know about, say, forces between skyrmions, you could use approximation like this to find out how is the energy varying with the separation and other parameters, so internal phases and so on. And also for quantization. When you want to quantize these things, you want to really have a good handle on a space of field configurations that you can quantize. And this gives you one way of producing that. So the bad thing is that I've already mentioned is this ODE that you need to solve to calculate this holonomy. You can only solve it explicitly for a spherically symmetric skyrmion, and in all other cases you have to compute it numerically. So there is a numerical step involved in this, computing this holonomy. So what we'd like to do is to sort of be able to get around that step that requires doing that bit numerically. In other words, we don't really want to have to solve this ODE numerically. So I'll now tell you in the last 15 minutes about a new approximation. So I've done with my review bit. This is a good time to ask any questions if there's anything that's not clear. Okay. If not, I'll tell you about the new bit then. So the new thing is, it's kind of like an ADHM type construction of skyrmions. So it's going to again give approximations to skyrmions, but it's going to do them directly from this ADHM data without having to solve a differential equation. And it will give rational approximations. So the skyrmions will be rational functions of the Cartesian coordinates. So here's the derivation of the new approach. Let's start with this equation that we don't want to have to solve. So this one given in yellow here, for this omega. So this differential equation in the fourth direction. And we're going to take that our gauge potential comes from the ADHM construction. So I can set A4 to be this expression in terms of psi. So let me stick that in. So that turns the yellow equation into the white one below it. That's the equation I have to solve. So let me discretize this equation. So I'm going to replace x4 which covers the whole real line, by a lattice. So I'm going to have a lattice of P points. So let's call them T1 to TP. Where I've got to cover the whole line. So T1 is just formally minus infinity and the TP is plus infinity. In other words, I've got a lattice where one end is minus infinity, the other end is plus infinity, and then I've got finite number of P minus 2 finite number of points in between. And let's do a forward difference approximation on this differential equation. So I'll just replace everything by all the derivatives. So there's a derivative on both sides. Let me replace it by simple forward difference approximation at a lattice point. And then I can use the fact that psi has unit length to see that one of those terms on the right-hand side is a psi dagger psi, and that becomes a 1, and then that cancels with the term on the left-hand side. So you see that once you discretize this lattice equation, says that down in the bottom right, it says that the omega at the next lattice point is the omega at the previous lattice point multiplied on the right by something that involves size. And since we start right at minus infinity with psi being 1, that says, you're just going to get psi at the other end, just going to be so omega at the other end, start with omega being 1 and being the identity at minus infinity, and you want it at plus infinity, and to get it, you're just multiplying on the right by a load of size. So the thing that we want, as written here, the omega at plus infinity is just a product of loads of psis and psi daggers at these lattice points. But also at plus or minus infinity, we know what psi is, because at plus or minus infinity, the gauge potential becomes trivial, and the kernel of psi is given by just taking a 1 in the first entry and 0 everywhere else. So that gives a final, the middle equation here. The omega that we want when we get to the top end, x4 is plus infinity, is product of size at the interior point, lattice point, sandwiched between these constant vector. Now here's something useful that maybe you won't know because I've only just told you about the ADHM, but it's not too hard to show, is that you see all these things sandwiched together. I've got psis and psi dagger. So psi on the left, psi dagger on the right at the same lattice point. Well, at any fixed point, psi dagger, I'm going to call that Q. That's a projector onto the kernel of delta. It's easy to check. So that means it can be written explicitly in terms of delta itself, the ADHM operator, without having to refer to psi at all. And here's the expression for it. So Q is written, at any point, is written here in terms of delta. So delta dagger delta here, remember delta is quaternion, but delta dagger delta is real. That's part of the ADHM constraint. So the only thing I have to do is some real linear algebra. I have to work out the inverse of this real matrix. But it's just linear algebra, so I can explicitly read off Q given the ADHM data. So it's just evaluating ADHM data somewhere. That gives me the Q. And so my omega that I'm interested in is just a product of Qs that I can read off explicitly from the ADHM data. And so this looks like a good numerical scheme. And normally with numerical schemes, you would say, I'll take loads of lattice points, make a very fine lattice, and that will be a good approximation to the continuum, which is the equation I was trying to solve. So here, my crazy idea is to do exactly the opposite of that. Is to, rather than use lots of interior lattice points to make it a very good approximation, I'm going to use hardly any. I'm going to do an ultra discretization of this. I'm only going to choose 3 interior lattice points. Our lattice points are going to be 0, so the x4 is 0 and x4 is plus or minus mu, where mu is some positive real parameter. So I'm going to sample the instanton only at x4 equals 0 and x4 is plus or minus mu. So that formula that involved calculating a product of Qs at all the interior lattice points now only has 3 Qs in it. So it's a much simpler formula, it's given here. Notice that I did some forward difference approximations. So I did various approximations. So the thing that I calculated should have been a unit quaternion, which I can think of as an element of SU2. But it won't be because I have some errors in the difference approximations. So I have to divide through by the modulus of the quaternion that I've calculated to recorrect for that and make sure it's a unit quaternion. So if you look at the expression that you had for Q, remember Q is just reading off stuff from the ADHM data. So this would give you something that's just rational. But because I have to do the modulus on the bottom, then you would think that will look algebraic. When I'm taking the modulus, there's the square root of something. So this looks like it gives me an algebraic expression. But in fact, it'll turn out that in all the examples I'll show you, it's actually rational. And it's one reason you can understand that is that all the instantons I'm considering, their ADHM data, has an axial symmetry in the X3, X4 plane. And you can show that that axial symmetry implies the relation given there for the Qs. So there's a Q relation. And you can prove that that shows that U is rational in the Cartesian coordinates. In other words, if you have this relation, the thing that's there is actually the square of something else. So that when you take the square root, that just cancels off the square and you still end up with something without square roots in it. So you might say, why on earth would you do this crazy idea and use only a few lattice points? And the reason is that you can do this analytically. So rather than having a numerical scheme, I'm going to, which would have lots of lattice points in it, I'm going to give an analytic scheme by taking only a couple of lattice points, small enough number of lattice points that I can do this explicitly and analytically. Okay. So let's see what you get. So basically everything now is just showing you what does that formula produce in yellow if you take the various ADHM data that describes the instantons, the ones you want to describe the skyrmions. So charge 1, the ADHM data, remember the square bit was an n by n matrix and we want n to be b to be 1, so it's a 1 by 1 matrix, in other words, just a number. And I'm taking the number to be 0, so it's a quaternionic number, of course. I'm taking it to be 0 because that means I've put my instanton at the origin. So the only thing there is left is a scale. So lambda is the size of the instanton. So if you plug into that formula I just had, it involves evaluating the ADHM data at various places, and you get that expression there. So notice this is a hedgehog ansatz with a profile function that's given here. So it's given in terms of I now have lambda, the size of the instanton, like I had before, and I also have this real positive constant mu, which is my sample point. So here I've got a new profile function. If I choose my parameters correctly, so the size of the instanton and the sample point, then I get something that has an error of only 0.3% compared to the true numerical value. The Tiamantan approximation was already good. That was an error of 0.9%. This does even better. It's 0.3%. And that's the final plot on this plot that I've been showing you. This is the profile function, the blue one that you get by using our new scheme. So you can see the blue one is incredibly close to the black one, which is the true numerical one. And you can see why the error is sort of only about 1/3%. Actually, if you spotted that the numbers that I took were so the scale and the sample point were very close to 2 and √2. And in fact, you don't lose anything in terms of the accuracy of the approximation. That energy that I showed you is the same to that level of precision if you take 2 and √2, which makes the formula look a bit nicer. So here's the explicit form for an approximation to the charge 1 skyrmion that is a rational function, and it has energy that's only 0.3% above the actual numerical one. Let's look at charge 2 and let's try and get an explicit approximation to a rational approximation to the axisymmetric charge 2, so this donut. You can do that if you take the ADHM data shown there. So now we've got a 2 by 2 block of quaternions at the bottom. and we stick a row of quaternions on top. Again, there's a size parameter. I'm going to take the size parameter to be 2 and the sample point to be 2 because they're very close to what you get if you try and search for the best ones. And I'm going to write here's the explicit rational expression for the Skyrm field. So I've written it in the form of unnormalized fields there, and there are all the components. So again, the components here, the unnormalized components, are all just polynomials. And then the thing that's on the bottom is the square root of something, but you can check with these explicit expressions that that thing inside the square root is itself a square, so you don't get any, so it becomes rational, not algebraic. So again, explicit expression, and this, again, you can ask, what's the error here? So this is the picture of what the energy density looks like. It's a good approximation to that toroidal case. The energy is remarkably close to the rational map approximation, the energy. They're both about 2.5% above the true one, above the actual energy, which makes it about, the error for the Tiamantin approximation is only about half that, but of course the Tiamantin approximation requires doing some numerics. You numerically have to solve the differential equation. The rational map approximation also requires a little bit of numerics because you need to numerically find the profile function that goes in there. So the fact that we get something that's basically the same accuracy of the rational map approximation, but there are no numerics at all involved, it's an explicit formula, is pretty good. And here you can take the ADHM data, this form, charge 2 data, with an extra parameter in it, A. This ADHM data will describe charge 2 skyrmions that include, it's a family of them, include well separated, the axial charge 2 that I've already shown you, and everything in between. So A between -1 and 1 controls the separation. So A equals 0 just goes back to what we had. That's the axisymmetric. And as you increase A, the 2 skyrmions separate out along the x-axis. As A tends to 1, they go to infinity. And so you can see they look very much like snapshots of the movie that I showed you from full numerics. Taking A negative separates them out along the y-axis. There is an explicit expression for the fields as rational functions. You can find it in the paper, but I didn't want to inflict it on you at this in this talk. But you can use this to for example, to calculate the energy as a function of separation for the 2 skyrmions. So here's a plot. You see it's minimal when they're on top of each other, and it increases as you separate them out. The dashed line is twice the energy of a single skyrmion, so it should tend to that as the separation tends to infinity. Okay, so I've got 2 minutes left to conclude. So what have I told you about? Skyrmions deform. I've hopefully shown you that skyrmions deform a lot, and when they come together, when they overlap, they deform each other and form these very symmetric shapes. And there are various approximations that are valid in different regimes, whether they're well separated, some work when they're on top of each other, others work. And what you really would like is one that works in all regimes. And we've been able to find one of those by introducing a new approximation, which is a sort of type of ADHM construction that allows you to describe all those and give you explicit formulae. I said I was doing something very crazy by taking only 3 internal points. You can do something even crazier, which is just take 2 internal points. So I was sampling at 0 and plus or minus mu. I could throw away the sample at 0. I could just sample at plus or minus mu. So just use 2 internal points. That also works. It gives you algebraic skyrmions rather than rational ones. So in this case, the thing inside the square root is no longer the square of something. But the formulae are a little bit simpler because the degrees of the polynomials are less. And you can find details of that in the paper too. As I mentioned, one of the motivations for this is applications. So we now have some explicit way of describing some moduli spaces in terms of explicit formula, and that's useful in quantization and in trying to match to the nuclear force. So I'll finish there. Thank you.
Yes, thank you very much for the fantastic talk.